Good afternoon. I hope we're all doing pretty well. Today, we're going to be working again with electric fields and electric potentials, and we'll be looking at a little bit of circuit problems. First things first, I want to talk about electric fields and electric potentials and how these two things are related to each other. So I'm going to imagine that this dot right here represents just a positive charge. And from a positive charge, electric fields radiate out every direction, right? So we have our electric field lines like that, right? Not a big shock, and we know that our electric field from a point charge E equal to KQ over R squared. Not too bad. We see that our electric field gets weaker as we get further away. And this makes sense to us because our electric field is related to force quite intimately by force is equal to Q times E. Another relationship I want to put on the board. So we have these relationships. But what does electric potential look like? We can map out electric potential at a bunch of different regions. And if we take a point, maybe a distance, represented by this blue R, away, well, the electric potential at that point, V, is equal to KQ over R. Yeah. What happens if we, instead of going to the right a distance r, we go up a distance r? Go right there. Well, it's going to be the same value of potential. R hasn't changed. It's the same value of potential. You go a distance r to the left, same value of potential. And in fact, at each of these points that are exactly a distance r away from our charge, we get the same potential. We can connect all of these points. Connect all of these points and we see that it forms sort of circle around our charge. And anywhere on this blue circle that I just drew, anywhere on this blue circle, we get the same value of potential. We call this an equipotential. Equipotential means equal potential all around, right? And we can form many of these. We can form a great many of these by just taking this different distance r's, and we see that all of these will form circles around them. Now, why is this important? Why this is important is because if we have these equipotential lines, we can see that they're related to the electric field, and we can see that their direction is perhaps related by the fact that electric fields always seem to be perpendicular to our equipotential lines. This is always going to be true. Electric fields are always perpendicular to equipotentials. And then the question becomes, well, why do we actually care about this at all? Why does this matter? Why do we care about equipotentials? Well, equipotentials, as we'll remember, are related to energies. E is equal to Q, potential energy U is equal to potential times Q, right? So what this is actually describing are areas where we are either increasing or decreasing potential energy, depending on the positive and the charge at the center. And this tells us that our electric fields are pointing in a direction where our potentials are decreasing. Our electric field is pointing in the direction of our decreasing potentials. This is also the same as saying our force is going to be in the same direction as decreasing potential energy. Things want to move towards decreased potential energy. Now, mathematically, there's a way to describe this. And the way to describe this is remembering how we got to potential energy from force. You guys remember a couple weeks ago, we did this derivation to get to energy, saying that the energy we use work, which is equal to negative potential energy. Work is equal to integral F dot dr, right? Well, if we want potential energy is the negative of that, so U is equal to negative F dot dr. Fantastic. Potential energy is related to the integral of force. That means if we wanted the force from potential energy, we would take the derivative of U, right? Just do the exact opposite. Well, similar relationship exists between potential and electric field. If you take the integral of electric field dot dr, we get a value for our potential. E is equal to negative integral, what was it saying? E dot dr. Now, this is somewhat useful, but not entirely. And the reason why this is not entirely useful is because, physically speaking, potentials are easy enough to measure. You guys have been in labs, right? And in our labs, we've measured electric potential. We've measured voltage several times. This was a really easy thing for us to do. So finding our voltage, really easy. Finding electric field, that is not something we can easily measure. We cannot easily measure electric field. Electric field is, after all, just some mathematical construct we use to talk about forces. So a better way to look at this is that instead of V is equal to integral E dot dr, we say that our potential V is equal to, nope, about to rewrite the same exact thing. We'd say that to find our electric field, what we want is the derivative of potential with respect to distance r. Minus sign carries along. Well, this is true. This is true, but we use a different way to talk about this because E is a vector. And if we want the vector, this actually gives us the r hat component, the radial component. And maybe this isn't so useful. So we like to maybe write this a different way. We say that the x component, this is for our class, this is just a little bit easier for us to deal with. For our class, the x is equal to negative dvdx. Take the derivative of potential with respect to position x, we get the x component of the electric. Same thing for y. We take the y derivative of potential, we get the y component of electric field. Z component of electric field is the z derivative. We can combine these all, and we will do this in the future. But for right now, we're just going to stick to this one dimension. We'll leave 3 dimensions for a future subject. But right now we're doing this. This is the first time that I'm going to be asking you to specifically do calculus in this class. You will have to take derivatives in this class. The derivatives I'm going to ask you to take are going to be of the form Howard rule derivatives. We should be somewhat familiar with this. Something like the derivative of some function, maybe I don't want these 3. 5x cubed, something like that with respect to x. Our rule is something we should be familiar with. I'm also going to ask you to do exponentials and logarithms. I'm not asking you to do that today, though, but something to be aware of, something to make sure you brush up on if you need to. Any questions about that? Any thoughts, comments, concerns? So we'll be doing good. Nothing too difficult. Nothing too difficult. Going back to this question, going back to this model for electric potentials, looking at these electric potentials. Well, let's say we put a charge. Let's say we put a charge right here. And we take that charge, we move it around. Let's say it goes on some path. It goes, doesn't really matter the path. Let's say it goes over this way, down through here, back to its original path. Well, during this process, it traveled along an equipotential line. So from here to here, no change in potential. From here to here, it went from a lower potential to a higher potential. Here to here, no change in potential. Here to here, went back down to lower potential. Throughout this entire process, the change in potential is equal to 0. Because the net gain of potential is equal to the net losses. In other words, in a closed path, I'm writing this really big because it's very important. In a closed path, change in potential delta V is equal to 0. This is the fundamental rule that forms what we call Kirkoffs loop rule. Kirkoffs loop rule says that for any charge, doesn't matter the situation, for any charge in a closed path, in a closed loop, meaning you start and end at the same spot, doesn't matter the route we took to get there, starting and ending at the same spot, that means delta V is equal to 0. Because this is true because potential only depends on where a particle is in that moment. It doesn't depend on how it got there. And this applies to circuits. Because in a circuit, we have charges that undergo a full loop. We have, for example, battery, resistor, going back to battery. We imagine a charge starts at the battery, goes through the resistor, goes back to the battery. And Kirkoff says that under that whole path, our delta V is going to equal 0. So we look at our charge starts here. When we apply this rule, we just pick some location. It doesn't matter where we begin, where we end, or it doesn't matter where we begin as long as we end at that same location. So we pick this blue spot. So our charge is going to go up. It's going to hit this resistor. And what resistors do, they drop voltages. So we say that this is going to give us a voltage drop. I've used that phrasing before in this class, but it drops our voltage. It's going to go around our circuit. It's going to hit this battery. What do batteries do? Battery gives us a gain of energy. Battery supplies us with energy. So this gives us a voltage gain. After the charge gains some energy from the battery, proceeds to its original position. And Kirkoff tells us that our voltage drops must be equal to our voltage gains. Ohm's law tells us that for a resistor, our voltage drop, our delta V drop for a resistor is equal to the current times the resistance, I times R. Our batteries have defined voltage gains. Delta V gain is equal to the battery's voltage. And we use this squiggly E to represent the EMF of a battery. EMF is just a fancy way to say the total gain in voltage from a battery. We have a 9-volt battery. The voltage gain, the EMF, is 9 volts. We have a 12-volt battery, 12 volts. So we apply Kirkoff's loop rule here, and voltage gains, EMF is equal to IR. That means this equation. Now on this circuit does not do that. But there's a couple of things that we need to take into account when applying this. And one of the most important things to take into account is directionality. We have to keep in mind that the direction that a current flows through a resistor is important. The direction of the current is important. The direction the battery is facing is important. Our voltage gain is positive when our path leads us from the negative, from the short side of the battery, to the positive. So for a battery, delta V is positive, it's greater than 0 when going from negative to positive. We take the negative value if we travel through it in the opposite direction. If we travel through it going the opposite direction, we have the negative. Resistors delta V is going to be positive if we travel with the current. Now this does assume something very specific that we're doing, and this is going to depend on sort of the resource that you look at. Because this assumes that we're using Kirkoffs loop rule in the form of voltage gains equal voltage losses, voltage drops. This is going to be true. This positive and positive terminology is going to be true if this is the form that we use. There's another form, just to make this a little bit more confusing for you guys. There is another form that says, instead of looking at Kirchhoff's loop rule like this, we say that the sum of voltages in a closed path is equal to 0. And I want to implore you guys to try out these two different methods, see what makes sense to you. For me, this is what makes most sense. Voltage gains equals voltage drops. That's what makes sense to me. And the reason why that makes sense to me is because I always think about it as looking at it as it goes through a sort of closed loop path outside of a circuit. For a lot of people, this is what makes sense. And if this is the terminology that you use, then what you're going to say is that 0 is equal to the voltages, the negative voltage drops. I don't know. 0 is equal to the voltage drops plus the voltage gains. You see that this has a sign difference when compared to this. That sign difference is now that our voltage drops are negative. So this form assumes that voltage drops are going to be less than 0 when traveling with the current. Exactly opposite. So depending on the way you want to look at it, whether you use voltage gains equals to voltage drop, something that's more familiar to myself from looking at it as a purely mathematical standpoint, not necessarily from the standpoint of circuit building, or do you want to look at it as just the sum of all voltages equal to 0, understanding that your voltage drops are going to be defined as negative. If you have a circuit that is more complicated than just a single resistor, it's going to be the case in most circuit problems you're given, probably all circuit problems you're given. We're past the point of dealing with a single resistor. We're going to be looking at multiple resistors. We're going to look at multiple loops in the future. That's combining loops and junctions. Right now, a couple of resistors here. To apply the loop rule, what we're going to do is a few steps. We're going to first guess direction of currents. Direction of currents are going to be guessed. Now we can make educated guesses. We can identify in a lot of these cases the direction current will flow. Here we might guess that current flows across these resistors left to right, because that seems to be the way that the battery is pushing them. Sometimes it's not going to be so obvious. But guess what? It's okay. It's okay if we guess the direction wrong. Because if we guess the direction wrong, we're going to end up with a negative current. And that just tells us, yeah, you got the direction wrong. You got the magnitude right, but the direction is wrong. We assume the wrong direction. So that's step 1, guess direction. Step 2, you're going to pick a starting point. Again, it doesn't matter where we start. We can start here, we can start in the middle of the resistors, we can start over there, doesn't matter. It's up to you to decide where to start. But until you get familiar with Kirchhoff's loop rule, I'm going to implore you to really actually draw out a dot where you are starting. and draw the line through the circuit, identifying your path that you're taking. Now, the path we take doesn't matter. We can choose to go from this point to the right, or we can choose to go down. Either way is totally fine. We choose to go to the right maybe because that's the direction of the currents, and we go around. And as we go around, we make sure we end at the same point. We never remove our pencil from the paper. We have to travel through. We can't skip any resistors or any components. And as we go along, we identify that voltage drops happened here by the resistor, voltage gained by the battery. Figure out whether those are positive or negative values. You either sum them up to 0 or set the voltage gains equal to the voltage drops. Both of these will give you the same answers. And why do we do this? Why does this matter? Well, this technique allows us to figure out what the current should be going through a resistor. When we build circuits, we get to decide what batteries we use. We get to decide what resistors we use, but we do not get to directly decide the current going through them. And that can be an issue because a lot of components will do specific things depending on the current that they get. Current is what matters to electrical components. So we want to be able to identify how much current is going through these components. So this takes us from a point where I'm just telling you, these are the voltages going across resistances, to a more realistic scenario of you building a circuit, you picking the components to satisfy a certain current. So these problems that you're going to see are going to mostly be of the form, given the circuit, figure out the currents going through the resistors, because the current tells us what's going on, how much energy is being released, how much heat is being dissipated by a resistor, et cetera, et cetera. We're going to see those later on. But knowing current is a very important thing in circuit analysis. Today, you guys are going to be working on a couple of problems. You're going to be working on a few problems involving Kirkoffs loop rule. Give you practice with some basic circuits. You guys are going to be working on problems involving solving electric field given some potential, and also figuring out some function that represents potential. You guys are going to be working on the other problem. I already forgotten the other problem I gave you guys. Oh, you're going to be doing another problem involving an infinite line of charge, but looking at it from a different perspective. We got to get comfortable with thinking about things in terms of the z-axis. We'll be using the z-axis a lot of the semester, no more just x and y planes. So I'm giving you a problem involving an infinite line of charge that spins into the z-axis, but the mathematics behaves exactly the same as it was before. Are there any questions before I set you guys off on your way to solve problems? Okay, as you guys solve problems, I want you guys to think about both of these sort of definitions of Kirkoffs junction rule. I want you guys to try them out, see what makes sense to you guys. See if either of them makes sense to you. And of course, as always, ask for help if you guys need it. Not what I wanted. All right, here's your QR code. It's also on Canvas for you guys. So you guys can go to Canvas and get it. Now Alex and I will be walking around helping you guys as needed.